Hello, this is Peyton Schmidt from D6 Engineering, and today I'll be presenting to you the Cube Manufacturing Process Development and Commercialization, a feasibility report. Our team consists of Bryce Taft, Tanner Russell, Tyler Sleeman, Kyle Lyle, and Peyton Schmidt. The scope of the project is to develop a manufacturing process for these cubes, determine a factory layout, source and spec necessary equipment, validate the process. Our constraints are we must be within budget, the product must meet print dimensions, and we must meet the schedule of 0 to 6 months, we'll produce 100 units per week. From 7 to 12 months, we'll produce 200 units per week. And from 13 to 18 months, we'll produce 400 units per week. And criteria is it should be commercially viable, it should be manufactured in the USA, and we should ramp to meet weekly run rate. The purpose for these cubes is that so robotic tenders with suction cup manipulators can grab and pick up and sort these cubes via color and via the 2D matrices on the sides. So they need to be roughly 1.5 inches. They need to be light enough to be picked up by the suction cup as well as flat enough. They need to be able to protect the embedded matrices and numbers from wear being handled. There needs to be no sharp edges, so if people do handle them, they do not hurt themselves. It needs to be corrosion and abrasive resistant, and it needs to be in 4 distinct colors so the robot tenders can differentiate in different ways. We were given small foam dice that were originally being used for this purpose, but they were too light and they get thrown everywhere. For our primary process options, we had to determine whether it was better to do a weekly delivery of material so we could decrease storage size, or if we could order it all at once and able to store it if we have enough room. We determined that it is better to order all of the material in bulk. We have more than enough room in our factory to handle and store all of these while the production takes place over 18 months. We also determined that it was better and more cost-effective for the vendors to cut material to size. It costs approximately $600 to bulk order all of our pieces in 48-inch sections, versus buying a cold saw, which is double the price at about $1,200, plus the consumables on that. And we would only ever need to rent a forklift once for our incoming delivery because we're only ever getting one delivery. Now, for our manufacturing method options, we looked at 4 different possibilities. We had 3D printing, a dual spindle lathe, sheet metal fabrication, and normal CNC milling. 3D printing was fast, however, it lacks dimensional accuracy. The dual spindle lathe has a lower material cost, higher precision, and minimal tending, which is very good. Sheet metal fabrication is low cost in equipment, but a lot of labor input. There's not very much automation with that. And for milling, it's very similar to the dual spindle lathe, but it's not as automatable. You have to have a person running it the entire time. So we ended up going with the dual spindle lathe, but here are some numbers that you can look at for a bit to determine what we came up with. These are rough early numbers we did research for, but the gist is resin 3D printing is very cheap to get into, but the material cost is high, but it's very fast. Still, there's that problem with the dimensional accuracy, which is why we ended up not going with it. The CNC mill, very similar to the dual spindle lathe, a little cheaper to start up, but twice as long to produce, as well as you have to consider that there's a lot of labor costs going into the CNC mill, along with sheet metal fabrication. Now, it's half the price of the CNC mill, however, it's a lot more per cube, as well as the time to make the cube and the labor costs are way higher. And then finally, the dual spindle lathe, which isn't quite as fast as the resin printing. However, it's fully automatable to the point where we just have to load it and press a button and go. And it's the cheapest material possible. For our finishing processes, we could have gone with powder coating or anodizing in-house or out-of-house. In the end, we ended up going with powder coating for its more uniform and strong finish, as well as it requires less sensitive chemicals and different things being regulated. And we ended up going in-house with this because powder coating materials and equipment are readily available and not too expensive. And it just lowers the chance that we're depending on another vendor to get our products done in time. For engraving our cube with the 2D matrices and the numbers, we decided to go with a laser engraver. It's the only thing that's automated is the actual engraving. We just plan on having some of our workers, while they're not busy, flip the cubes. It takes about 10 minutes per 30 cubes, and they'll have to do that 6 times for each side, so they'll just flip it every time. This is our process flow. So it goes from storage to loading the lathe to operating the lathe to moving to the cleaning cell. We are going to rinse and dry it. We do an inspection where if it fails, we either go back and fix it or scrap the part. If it passes, we load it onto the rack to be chemically treated and then dry it in an oven and then powder coated and then re-cured in that oven. There will be another inspection at this point where if it fails, it will be scrapped or reworked. And then those will all go to laser engraving if they pass, where there will be a final inspection. And then we'll move to the packaging and shipping cell where they'll be packaged and labeled and shipped. Our cell layout is fairly simple. We have a machining cell, which is just the Haas ST15Y dual spindle lathe, as well as the bar feeder. We're using the bar feeder more as just a way of making the lathe more able to automate. It's not actually going to load the bars, it's just going to be handling the bars. And then the post-processing cell is where everything else happens, the degrease and rinse, the inspection benches, the prep for powder coating and phosphate, the parts oven, the spray booth, the next inspection bench, and the laser engraver. Our facility layout is fairly simple. Those cells from the last slide are just placed in here. We have 2 phases. The first phase is more than enough to produce our cube requirements for the first 18 months. If we do need to expand, we can buy another set of cells, and then that will expand into phase 2. We have more than enough room to store all of the stock for the 18 months. However, there is also more room just in general if we were to order more than that. For our machine cell capital costs, our investment is about 170,000, and then the initial round of consumables is 1.2k. So the total startup cost is going to still be around $170,000. But this includes the bar feeder, the lathe, and the collets that we need to work with square stock. Our post-processing cell capital costs are about $20,000, and that's for everything, including the racks, the ovens, the booths, the laser, the spray equipment, everything we need. These are our machining requirements. It shows the total tack time is 360 seconds per part, and the different estimated downtimes and machine times. We've got our cycles and loaded machine times, and these are all done in batches of 30. For the process validation and discrete event simulation, we made a model in Arena, and this just shows the process flow like before, and it runs with simulated downtime, the scheduled work hours, as well as the time between stations. Now is also a good time to mention our working hours and salaries. So both of our employees, our owner and our operator, both work 8 hours a day. The operator starts 1 hour earlier than the owner. The owner operator is paid $50 an hour, and the regular operator is paid $20 an hour. Finally, for our financial analysis, our total cost is about $500,000. And with a contract quantity of 16,800 cubes at an MSRP of $100 each, we're going to make a revenue of about $1.7 million and a total profit of about $1.2 million. The ROI for a single contract is going to be 151.11% with a depreciation over 5 years. That's a payback period of 2.4 months. So, these cubes are a gold mine. This process is economically viable and satisfies the customer requirements. D6 recommends proceeding. Thank you.